Today we are going to be learning the product rule for derivatives. We learned in previous sections that the derivative of a sum or a difference is simply the sum or difference of the derivatives. We do this all the time. If you're adding two things together, you just take the derivative of each piece and add those together. Easy. We do it all the time. What's the derivative of this function? This is actually the sum of several functions, right? We can think of this as the sum of four different functions. So we just take the derivative of each piece and add those together. And we're done. So what if instead of a sum or a difference of terms, we have a product of terms? What if we have the product of two terms or more? How do you take the derivative of that? Is it as simple? Is it as simple as just taking the derivative of each piece and multiplying it together? The short answer is no, but I want to prove that to you and to show that to you. Not prove it, but show you why it wouldn't make sense to do that. Let's consider the derivative of this product. We have the product of two functions, 3x and 4x squared. So the question is the derivative, would that be the derivative of 3x times the derivative of 4x squared? Would this be 24x? Okay, well, I know that 3x times 4x squared is equal to 12x cubed. I know that that is true, right? So what is the derivative of 12x cubed? Is the derivative of 12x cubed 24x? Absolutely not. The derivative of 12x cubed is 36x squared, not 24x. So, hopefully this shows you that you cannot just take the derivative of each piece and multiply them together. Okay? Instead we have the product rule. So I'm going to leave this out here. We know that the derivative of 12x cubed, we know that the derivative of this product is 36x squared, right? I'm going to leave this for a second and come back. Okay, the product rule for derivatives looks like this. So if we're taking the derivative of the product of two functions, f and g, here's how you do it. Take one of the functions. I always just begin with whatever comes first and take its derivative. So the derivative of f is f prime. Multiply that by the other function left alone, plus, now do the other pair, the derivative of the second function times the first function left alone. That is the product rule for derivatives. Let's go back to our little example here. So if we apply that to 3x times 4x squared, let's take the derivative of 3x times 4x squared. I'm going to start at the first function and take its derivative, 3. I'm going to multiply by the 4x squared left alone, plus, now the derivative of 4x squared. The derivative of 4x squared is 8x, and then we multiply that by the 3x left alone. So this is 12x squared plus 24x squared, which is indeed 36x squared. Alrighty, so that is how the product rule works. Of course, in this example, I would not use the product rule for that. I would multiply those two terms together and take its derivative. It's much quicker than using the product rule. But there will be some functions that you have to use the product rule on. Or maybe you don't have to, but it's preferable to. Let's look at some examples. Okay, so for this, here's f of x. I could, if I wanted to, distribute and multiply these two trinomials together and then use the power rule on each term. But it's going to be quicker to take the derivative using the product rule. So we start at our first function, And since we have a plus sign in between here, you could indeed switch these two. But I always do the first one first, because tomorrow we're going to get the quotient rule for derivatives. And the quotient rule of derivatives, you have to do the first one first, the top first. So I always do the first one first. So take your first function and take its derivative. 4x cubed minus 6x plus 9. Multiply by the second function left alone, plus, say plus for product rule, plus for product rule. The quotient rule will have a minus, by the way. Okay, plus for product rule, and now we take the derivative of the second function, so 10x to the fourth plus 4x cubed, and multiply by the first function left alone, and we are done. So that is the derivative of the product of those two trinomials. Much less time than it would have taken to multiply, distribute, combine like terms, and take the derivative of each piece. Much quicker. That's the product rule. Okay, find the instantaneous rate of change. Instantaneous rate of change is the derivative of x cubed times sine x with respect to x in terms of x. In terms of x only means that you will have x's in your answer and no other variables in your answer. Okay, that's what in terms of x means. All right, so y is equal to x cubed sine x. We are finding the derivative, the instantaneous rate of change, so dy dx. You guys, average rate of change, AROC, is delta y over delta x. IROC, instantaneous rate of change, is dy dx. Instantaneous rate of change versus average rate of change. Okay, so back to this problem. I have the product of two functions, so I'm going to use the product rule to get the derivative. The derivative of the first term is 3x squared, multiply by the second function left alone, plus for product rule. Now we're multiplying, now we need the derivative of the second term, which is cosine x times the x cubed left alone. So this would be a safe stop spot. As a multiple choice question, they would write that as 3x squared sine x plus x cubed cosine x. Okay, so I get students asking me all the time, are these parentheses necessary? No, they are not. They're not exactly necessary. At least these are not necessary. I like to do that just to designate. It kind of reminds students that I just used the product rule. What you do not want to do on the second one, you would not want to write cosine x times x cubed. You would not want to write that because that is ambiguous. Is the x cubed part of the argument? It shouldn't be. And if you write it like that, it's ambiguous and it could be perceived as being part of the argument. So don't write it like that. Communicate your work. All right. Number 3, what is the slope of the tangent line? Slope of the tangent line is one of our meanings of derivative. So what is the slope of the tangent line to this curve at the point when x is pi over 3? Okay. Well, g of x is 6 sine x. Gosh, g of x is 6 sine x tangent x. All right. As we learned before, this 6, I could, if I wanted to, I could stick it with the sine x. I could, if I wanted to, make it sine x times 6 tangent x. Or what I sometimes prefer to do is make the 6 outside of the whole product. Let me show you how that would work. So for the derivative, any constant times a function, when you're taking its derivative, it's just that constant times the derivative. So I can leave that 6 outside of the entire product rule for the this derivative. And now I just take the derivative of sine x, which is cosine x, multiplied by tangent x left alone, plus for product rule. Now the derivative of tangent x, which is secant squared x, times the sine x left alone. So there is the derivative. In a multiple choice answer, they may or may not have this 6 factored out. If it was left in, it would look like this. Okay, so I can see that being a multiple choice answer. Or the 6 factored out. Sometimes they do that as well. Alrighty, number 4. Find h. Oh, I never did finish this. Goodness. It wouldn't matter how they wrote it because we never did plug in pi over 3 for x. G prime at pi over 3. Say what you're doing. It's no longer g of x. Because we're going to plug in pi over 3. Do not put an equal sign here and then plug in pi over 3. That's not true. You're telling me something that's not true if you say that. Okay. 6 times cosine of pi over 3 is a half. Tangent of pi over 3 is square root of 3 plus secant squared of pi over 3. Well, secant is the flip of cosine. Cosine of pi over 3 is a half. The flip of a half is 2. And 2 squared is 4. Secant squared is 2. When we put them, secant squared of pi over 3 is 2 squared, which is 4. And then sine of pi over 3 is square root of 3 over 2. That would be a safe stop spot. Let's clean that up a little bit. I'm going to go ahead and factor this, or multiply the 6 in. This is going to reduce and make it 3 square root 3. Here we have a 2 square root 3 times 6 is a 12 square root 3. So this is 15 square root 3. Okay, I think I added all that right. Hopefully I did. Okay. Find h prime of 2. H prime of 2. So first find h prime of x and then plug in 2 for x. Derivative of the first term is 3. Multiplied by the second term left alone. Plus derivative of the second term, 4x minus 8 times the first term left alone. Now plug in 2 for x. We'll have 3 times, okay, 8 minus 16 plus 1, and 2 for x here. That would be 8 minus 8. Oh, well that was nice. I just get 0. I don't have to worry about that other piece. So we have 3 times negative 8 plus 1 is negative 7, so negative 21. We can confirm these, you guys. You can confirm these on your calculator. And since we have such a short video here, let's confirm this one on our calculator. We're taking the derivative of this function at 2. H prime of 2. So math, and then down here at number 8, we've done this in class, so math 8 with respect to x of parentheses 3x minus 2, close that parentheses, times a new parentheses, 2x squared minus 8x plus 1, close that parentheses, and we are evaluating it at 2. And here's what it gave me. So who's more correct? Our work or their work? Know that there's no little person in this calculator finding derivatives. Okay, they're using a numeric process that will stop functioning as soon as it reaches the programmed tolerance level. So what you're seeing back here is a little error. Okay, it's the tolerance. It has reached its tolerance level. This is the exact answer. This is the calculator's numeric approximation. And it's a very, very good approximation. Okay? But when you read something like this, You need to interpret it as negative 21. Let's go do number 3. Since we have the extra moment, let's go do number 3. Okay, so the derivative with respect to x of 6 sine x tangent x at pi over 3. So I got 25.9808, blah, da, 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 da. Let's see if that is equal to 15 square root of 3. Once again, it is correct to 3 decimal places. It will always be correct to 3 decimal places. On the AP exam, we must write our answers correct to 3 decimal places. Okay, so our calculator will be correct always to 3 decimal places. Alrighty, so this was their numeric approximation. This is the exact. That is the exact. Alright, that is the product rule for derivatives.